Where is the p block in the periodic table? We are referring to columns 13 through 18 on the right-hand side of the table. Elements in the p block have their outermost or valence electrons in a p orbital. As you recall, there are 3 p orbitals in a p sublevel, and each orbital can hold a maximum of 2 electrons. This is why there are 6 columns in the p block. There is a simple relationship between the group number, the number of valence electrons, and the electron configuration. Group 13 has 3 valence electrons, and the electron configuration ends as ns2 np1. As we move across each column to the right, the columns or groups each gain an additional valence electron. The exception, of course, is helium, which has only 2 electrons. Within each of the 6 different families of the p block, there are significant variations in properties. Although all the members of the same family have the same number of valence electrons, their inner cores are different. The variations in the arrangement of the core electrons affect the physical properties, such as atomic and ionic radii, and ionization energies, as well as the chemical properties of the elements in the same family. For p block elements, the maximum oxidation state is equal to the total number of valence electrons. So, as we move from group 13 to group 18, the maximum oxidation state rises from +3 to +8. This is sometimes called the group oxidation state. For the boron, carbon, and nitrogen families, this is the most stable oxidation state for the lighter elements in each group. However, other oxidation states are possible for each group. Often, an oxidation number 2 away from the total number of valence electrons is stable. The stability of oxidation states that are 2 less than the group oxidation state are sometimes attributed to the inert pair effect. As elements get heavier down a column, the oxidation state 2 less than the group oxidation state becomes more stable. This does vary somewhat from group to group. Metalloids and non-metals are found only in the p block of the periodic table. Down a column, the non-metal character of the elements decreases. The heaviest element in each column has the most metallic character of that family of elements. There is a lot of diversity in the properties of p block elements. Since a given family may have metals, metalloids, and non-metals. Metals and non-metals have distinctly different properties. When comparing metals and non-metals, non-metals typically have higher ionization energies than metals. The electronegativities of non-metals are generally higher than that of metals. Therefore, metals readily lose electrons, forming cations. Non-metals typically gain electrons, forming anions. Compounds formed between a metal and a non-metal are essentially ionic in nature. This is due to the large electronegativity difference between the elements. The metal transfers an electron to the non-metal, and the oppositely charged ions that result are strongly attracted to each other. Compounds between 2 non-metals tend to be primarily covalent in character. The small differences in electronegativity result in a sharing of electrons. Oxides of non-metals are either acidic or neutral in nature. Acidic oxides, such as nitrogen dioxide, will form acids when dissolved in water. metal oxides are usually basic. For example, when magnesium oxide is dissolved in water, hydroxide ions will form. Let's focus our attention on the group 13 elements. The members of the boron family include boron, aluminium, gallium, indium, and thallium. The elements in group 13 exhibit a wide variety of properties. For example, boron trioxide is an acidic oxide. Aluminium oxide and gallium oxide are amphoteric. They can act as both acids and bases. The oxides of indium and thallium are basic. The first member of each family in the P block, that would be boron, carbon, nitrogen, oxygen, fluorine, and helium, have the smallest atomic radius in their respective families. Each of these exhibits some anomalous behavior as a result. For example, the elements in period 2 have a maximum covalence of 4. They never exceed 8 electrons because they can only use their 2s and 2p orbitals in bonding. For example, boron can form the complex ion Bf4-. The elements in period 3 and below can achieve expanded octets. Since these elements have unused d orbitals, they can have more than 8 electrons. Therefore, we observe the hexafluoroaluminate ion. We often observe that the first member in each group in the P block can form multiple bonds to itself and other elements in period 2. For example, carbon can form multiple bonds with itself as well as with nitrogen. These multiple bonds involve sideways overlapping or pi bonding of p orbitals. P block elements in period 3 and below can use d orbitals to create pi bonds. As a result, the elements in period 3 and below can achieve a higher coordination number than the first element in the group. The elements in group 13 will be the focus for the rest of this module. Boron is a fairly rare element. Less than 0.0001% of the Earth's crust by mass. This typical non-metallic element is found as a hard, black solid in its pure form. A photograph of boron powder is shown here. In addition to boron powder, boron occurs in several other allotropes, including crystalline boron and alpha boron. Only 2 isotopes of boron are found in nature. Almost 19% of boron atoms are found as boron-10, with 5 protons and 5 neutrons. Boron-11, which has 5 protons and 6 neutrons, is the most abundant isotope. In nature, boron is most frequently found in 3 compounds: orthoboric acid, kernite, and borax. In India, borax is found in the Puga Valley in Ladakh and the Sambar Lake region of Rajasthan. Aluminium is a metal, although it has many chemical similarities with boron. It is the third most abundant element and the most abundant metal in the Earth's crust, contributing 8.3% by mass. Important minerals of aluminium include bauxite, cryolite, and mica. the electron configurations of the group 13 elements all end as ns2, np1. For example, consider the electron configurations of boron and aluminium in noble gas notation. They both have 3 valence electrons. However, if we look at the electron configurations of the rest of the family, we see quickly that they are all more complex than for the s-block elements. This complexity affects the chemistry of this group. While boron and aluminium have core configurations identical to the nearest noble gases, as we saw just now, gallium and indium have 10d electrons in addition to the noble gas core. Thallium has 14f electrons plus 10d electrons in addition to the noble gas core. In general, atomic radius increases down a column. However, this trend is not uniform. Try to answer this question before continuing. Why does gallium have a smaller radius than aluminium? Answer: gallium has 10d electrons in addition to the noble gas core. These d electrons provide very little shielding from the nuclear charge, since d orbitals have little electron density near the nucleus. Thus, the outermost electrons in gallium are held more tightly than in aluminium. In general, ionization energies are expected to decrease down a column. For the group 13 elements, however, the expected smooth decrease is not observed, as shown in the table. This is due to the poor shielding by d and f electrons. As additional electrons are removed, the ionization energies for each removal increase. For example, the first 3 ionization energies of group 13 elements are shown. It should be noted that the sum of the first 3 ionization energies for boron is significantly higher than for the other group 13 elements. In general, electronegativities are expected to decrease down a column. For the group 13 elements, electronegativity decreases from boron to aluminium, then increases slightly down the column. This correlates with the deviations in atomic size observed in this group. The density of the group 13 elements increases down the family. Boron has a high melting point, 2453 Kelvin, due to its strong crystal lattice. The other members of the family are soft metals, with low melting points. The melting point of gallium is only 303 Kelvin, low enough to melt in the palm of your hand. Gallium's boiling point is very high, 2676 Kelvin, making it very useful for measuring high temperatures. Let's turn our attention to the chemical properties of the elements in group 13. With its small size and the high sum of its first 3 ionization energies, boron forms only covalent compounds. The formation of a +3 ion is unfavorable. The other members of the family, which are all metals, form +3 cations. Down the column, +1 ions become more stable. This is due to the outermost s electrons being held more tightly, and so only the electron in the outermost p orbital is lost. With 3 valence electrons, boron often forms compounds such as boron trifluoride, with only 6 electrons around the central boron. Such molecules are described as being electron deficient. They tend to gain 2 electrons to achieve a stable octet. Therefore, BF3 acts as a Lewis acid, that is, an electron pair acceptor. Try to answer these questions on your own before checking the answer. What is the hybridization of the central atom in BF3? Shown on the left. And for BF4 minus the product in this reaction. What is the geometry for each of these species? BF3 with a coordination number of 3 around the central atom displays sp2 hybridization. Its geometry is trigonal planar. In BF4 minus, there is a coordination number of 4 around the central atom. So, the hybridization is sp3. The geometry is tetrahedral. Aluminium chloride dimerizes to achieve stability. The dimer has tetrahedral geometry around the aluminiums. Trivalent compounds hydrolyze in water to form complex ions. Trichlorides in water form complex ions with 4 hydroxides around the central metal. In these ions, the metal exhibits tetrahedral geometry and sp3 hybridization. When aluminium chloride is placed in acidified water, complex ions form in which 6 water molecules surround the aluminium. These complex ions have an octahedral geometry. The aluminium is sp3d2 hybridized in these complex ions. Crystalline boron is unreactive towards air. Aluminium forms a thin oxide layer on its surface, so no further reaction with air will be observed, although aluminium is a fairly reactive metal. The group 13 elements form oxides when heated in air. For example, the reaction of amorphous boron and oxygen is shown here. When heated in nitrogen, the group 13 elements form nitrides. The synthesis of aluminium nitride is given here. Boron does not react with acids or bases. Aluminium is amphoteric. It dissolves in mineral acids, such as HCl, and it dissolves in aqueous alkali solutions. Aluminium reacts with dilute hydrochloric acid in a single replacement reaction, as shown here. Hydrogen gas bubbles out of the mixture. In the presence of concentrated nitric acid, aluminium forms a protective oxide layer on its outer surface, preventing further reaction. In the presence of hydroxides, aluminium reacts to form complex ions and release hydrogen gas. The group 13 elements, with the exception of thallium, react vigorously with the halogens to form halides. The reaction of aluminium with bromine is shown here. Try to answer this question on your own before going on. Why does aluminium form the octahedral complex ion A1F6-3, but boron doesn't form the BF6-3 ion? Answer: aluminium, in period 3, can use its unused 3d orbitals to achieve an expanded octet. Boron doesn't have any d orbitals, so it cannot expand its octet. Some important compounds of boron are borax, orthoboric acid and diborane. We will discuss each of them in turn. Borax is the most important boron compound. Borax is used as a flux in soldering and as a cleaning agent in leather industry and laundry. Found as a white crystalline solid, as shown in the photograph, borax is a decahydrate of sodium tetraborate that you see here. Borax actually contains the hydroxyborate ion tetranuclear units, illustrated here. Hence, the correct formula for borax is Na2B4O5 OH taken 4 times, 8H2O. Borax dissolves in water and the resulting solution is alkaline. As shown in the reaction, when borax is placed in water, sodium hydroxide is produced. When borax is heated, it loses its water off crystallization and swells. The resulting white, opaque mass is anhydrous sodium tetraborate. When the anhydrous sodium tetraborate is further heated, it becomes a transparent liquid. When solidified, this is referred to as borax bead, which contains sodium metaborate NaBO2 and boric anhydride B2O3. The borax bead test is a qualitative way to test for the presence of transition metal ions. A platinum loop is used to heat a small sample of borax in a Bunsen burner flame until a borax bead forms. The bead is then dipped into a small sample of the substance being tested. Then, it is held in the lower part of the flame, allowed to cool, and then heated in the upper or oxidizing part of the flame. The formation of a colored metaborates of transition metals identifies the presence of transition metal ions. For example, cobalt ions give a blue-colored bead in this test. Orthoboric acid is another important compound of boron. Its chemical formula is H3BO3. It is also a white, crystalline solid. Orthoboric acid is only sparingly soluble in cool water, but highly soluble in hot water. Orthoboric acid forms a layered structure. The molecules of orthoboric acid, which can be written as BOH, taken thrice, arrange in a plane, and the molecules link together by hydrogen bonds. Try to answer this question independently before proceeding. Why is orthoboric acid a weak acid? Answer. One definition of an acid is its ability to release hydrogen ions. Orthoboric acid is not a protonic acid and doesn't release hydrogen ions on its own. It acts as a weak loose acid. As shown in the reaction, it can accept an electron pair from water to complete its own octet, thereby releasing the hydronium ion. Since it is a weak acid, the Ka value of orthoboric acid is very low, of the order of 10 to the power minus 10. There are mainly two ways to prepare orthoboric acid. One way is to acidify an aqueous solution of borax. The balanced equation is given here. Another way to prepare orthoboric acid is the hydrolysis of boron compounds. For example, the reaction of boron trifluoride with water yields fluoroboric acid, HbF4, along with orthoboric acid. When heated above 370 Kelvin, orthoboric acid decomposes to form metaboric acid, HBO2. If metaboric acid is heated further, it will form boric oxide, B2O3. Diborane, B2H6, whose structure is illustrated here, is another important compound of boron. Boranes are a class of compounds containing only boron and hydrogen. Diborane is a colorless, highly toxic and extremely reactive. This colorless and highly toxic gas has a boiling point of 180 Kelvin. There are several ways to prepare diborane. One route involves reacting boron trifluoride with lithium aluminium hydride in presence of diethyl ether, as shown by this chemical equation. In the laboratory, oxidization of sodium borohydride with iodine produces diborane. Sodium iodide and hydrogen gas are the byproducts of this reaction. Try to answer this question on your own before continuing. Identify the oxidizing agent and the reducing agent in the reaction of sodium borohydride with iodine. Recall that an oxidizing agent is a substance that gets reduced. I2, which has an oxidation state of 0, forms an iodide ion with an oxidation number of -1. Since iodine is reduced, it must be the oxidizing agent. Therefore, NaBH4 must be the reducing agent. The third method for preparing diborane on an industrial scale involves the reaction of boron trifluoride with sodium hydride at 450 Kelvin. Sodium fluoride is the other product of the reaction. In air, diborane catches fire spontaneously. The reaction of diborane and oxygen is extremely exothermic, releasing 1976 kilojoules of energy for each mole of diborane. Boranes were once considered for use as solid fuels for rockets because of their exothermic reaction with oxygen. When placed in water, diborane undergoes hydrolysis to form orthoboric acid, as shown in the reaction here. Hydrogen gas is also released in this reaction. Diborane undergoes cleavage reactions with Lewis bases. In these reactions, the diborane molecule breaks apart to form borane adducts with the Lewis base. Two examples of these cleavage reactions are shown. One with trimethylamine and the other with carbon monoxide. Diborane can react with ammonia. Initially, the reaction of diborane with ammonia produces an adduct diammoniate of diborane. This exists in a slightly different form, as shown in the chemical equation. When this substance is heated further, borazine, B3N3H6, is formed. Note the alternating boron and nitrogen atoms in the 6-membered ring of borazine. Since it resembles structurally with benzene, it is called as inorganic benzene. Diborane is an electron-deficient molecule. Notice the peculiar structure of it. The 2 boron atoms and the 4 terminal hydrogen atoms of the molecule are all in the same plane. These 4 terminal BH bonds are regular 2-centered 2-electron bonds. The bridging hydrogen atoms lie above and below this plane. The 2 bridge BHB bonds are unusual 3-centered 2-electron bonds. The bond lengths are different as well. The bond length of the bridging hydrogen and boron is 134 picometers in length, while the bond length of the terminal hydrogens and boron is only 119 picometers. The boron atoms in diborane undergo sp3 hybridization. The overlapping of a vacant sp3 hybrid orbital of one boron atom and sp3 hybrid orbital of another boron atom containing one electron with the pure s orbital of bridging hydrogens containing one electron results in the banana bonds. Similarly, other banana bond is formed on other side. Thus, the 2 banana bonds formed lie above and below the plane of the boron atoms. The remaining 2 sp3 hybrid orbitals of each boron atom overlap with terminal hydrogen atoms to form normal sigma bonds. This results in the formation of 4 terminal hydrogen bonds. Boron forms a series of hybridoborates. One such ion is the borohydride ion, BH4-, which has a tetrahedral geometry. Sodium borohydride and lithium borohydride can be prepared by reacting the metal hydride with diborane, as shown in the equation here. Borohydrides are good reducing agents. Thus, they are widely used in organic synthesis, as well as to prepare other metal borohydrides. Boron has a number of applications. Because it is a hard solid with a high melting point, low density, and low electrical conductivity. Boron fibers are used to make bulletproof vests and light-weighted composite material for aeroplanes. The boron-10 isotope has a high ability to absorb neutrons. Therefore, metal borides are used as control rods and protective shields in nuclear power plants. Borax and boric acid are used in the manufacture of heat-resistant glass, such as Pyrex. They are also used to make glass wool and fiberglass. Borax is used as a flux for soldering metals, for heat, scratch, and stain-resistant glazed coatings for ceramics, and in the manufacture of medicinal soaps. Dilute aqueous solutions of boric acid can be used as mild antiseptics as well as an eye wash. Let's turn our attention to the properties of aluminium. Aluminium is a bright silvery white metal. It has a high tensile strength. It also has high thermal and electrical conductivity. In fact, its electrical conductivity is twice that of copper when compared on mass to mass basis. Aluminium forms a number of alloys with various elements, including copper, manganese, magnesium, silicon, and zinc. Aluminium and its alloys are readily shaped into pipes, tubing, rods, wires, or foils. Hence, aluminium and its alloys are widely used in packing, cookware, utensil making, construction, aeroplanes, and transportation industry. Recycling of aluminium is significantly less expensive than mining and refining aluminium ore. It's better for the environment too. So always recycle your aluminium cans. Group 14 elements, sometimes called the carbon family, are carbon, silicon, germanium, tin, and lead. In the Earth's crust, carbon is the 17th most abundant element. Silicon, the second most abundant element in the Earth's crust, contributes 27.7% of the crust's mass. It is easy to argue that carbon is the most versatile of all the elements. It is found in nature, both in its elemental state as well as in compounds. It is an essential component of all living things. Organic chemistry is the study of the compounds that contain carbon. The work of many talented chemists is devoted to this very important element. The element is found in several different forms in nature: coal, diamond, and graphite. It is found in a range of compounds in nature, including carbonates, hydrocarbons, and carbon dioxide. Since carbon can combine with sulfur, hydrogen, and chlorine, it forms a wide range of compounds that are used for everything, from medicines to plastics. Carbon is essential for a number of biologically important substances as well. Two stable isotopes exist for naturally occurring carbon: carbon-12 and carbon-13. Almost 98.9% of naturally occurring carbon atoms are found as carbon-12, with 6 protons and 6 neutrons in the nucleus. The remaining 1.1% of carbon atoms are carbon-13, with 7 neutrons in the nucleus. A third isotope of carbon is the unstable carbon-14. This radioactive isotope of carbon contains 6 protons and 8 neutrons in its nucleus. With a half-life of 5,750 years, it is used in radiocarbon dating. In nature, silicon is found in silica and silicate compounds. Silicon is a very important constituent of ceramics, glass, and cement. Germanium is found only in trace amounts in the Earth's crust. Germanium was one of the unknown elements whose existence had been predicted by Mendeleev based on the gaps in his periodic table. Tin is a silvery white metal, as shown in the photograph on the left, with several allotropes. When a bar of tin is bent, it makes a characteristic sound called the cry of tin. Tin is mostly found as the ore cassiterite, shown in the photograph on the right. Cassiterite has the chemical formula SnO2. Lead is a very soft, greyish metal that is shiny when first cut. Lead has been used since ancient times. But lead poisoning can cause many serious health problems, especially in children. Lead occurs in nature mostly as galena, which has the chemical formula PbS. Both germanium and silicon are important semiconductor materials. Ultra-pure samples are used to manufacture transistors and semiconductors. All the group 14 elements have 4 valence electrons. The electron configurations of all of them end as ns2, np2. However, despite the similar valence configurations, their inner cores do vary down the column as the D and F sublevels become available. In general, atomic radii increase down a column, and this pattern is observed for the group 14 elements too. The increase is substantial from carbon to silicon, but it is less pronounced from silicon down to lead. The slower increase from silicon to lead is a result of the completely filled D and F sublevels in the heavier family members. In general, ionization energy increases from left to right. The group 14 elements have higher ionization energies than the elements of group 13, as shown in the illustration. In general, ionization energy decreases down a column. Generally, this is true for the group 14 elements. But notice the small increase from tin to lead. This is due to the poor shielding provided by the D and F electrons, along with the increasing atomic radius. In general, electronegativity increases from left to right across a period. Notice that the group 14 elements are slightly more electronegative than the group 13 elements in the same period. In general, electronegativity decreases down a column. However, silicon, germanium, tin, and lead all have very similar electronegativities. In terms of their physical properties, all the group 14 elements are found as solids. Their metallic character increases down the column. Carbon and silicon are both non-metals, whereas germanium is a metalloid. Tin and lead are both soft metals with low melting points. The melting points and boiling points of the group 14 elements are much higher than the corresponding group 13 elements. For example, silicon has a melting point of 1693 Kelvin. But the melting point of aluminium in the same period is 933 Kelvin. With their 4 valence electrons, the group 14 elements typically achieve either a +4 or a +2 oxidation state. Compounds with a +4 oxidation state are generally covalent in nature. Because of the high sum of the first 4 ionization energies for the group 14 elements. Carbon and silicon are more likely to be found in a +4 oxidation state. It should be noted that sometimes carbon is found with negative oxidation numbers. Try to answer these independently before checking the answers. What is the oxidation number of carbon in each of the following? Methane, CH4. Carbon dioxide, CO2. Ethine or acetylene, C2H2. Assigning oxidation numbers is an important skill. In methane, the carbon is -4. Remember that in compounds, hydrogen often has an oxidation number of +1. And the sum of the oxidation numbers must be 0 for a neutral compound. In carbon dioxide, the carbon is +4. Each oxygen has an oxidation number of -2 here. In ethine, the carbon is in a -1 oxidation state. Again, each hydrogen is +1. So the carbons must be -1 for the sum of the oxidation numbers to be 0. The heavier members of the family are more likely to show +2 oxidation states than the lighter members. This is because the outermost s electrons, which are paired, don't participate in bonding. Thus, it is observed that germanium most commonly exhibits a +4 oxidation state in compounds, and only rarely a +2 oxidation state. Tin is found in both +2 and +4 oxidation states in compounds. For example, the tin 2 chloride and tin 4 chloride forms. Tin in a +2 state is a reducing agent. That is, tin 2 tends to lose 2 electrons or oxidize to achieve a +4 oxidation state. Remember that a reducing agent is the species that oxidizes itself. Lead forms stable compounds with a +2 oxidation number. Compounds with lead in a +4 oxidation state are strong oxidizing agents. This means that lead-4 can gain 2 electrons, forming the lead-2 ion. Remember, the substance that undergoes reduction can be called the oxidizing agent. Tetravalent compounds, such as carbon tetrachloride, have 8 electrons around the central atom. Carbon always obeys the octet rule. Such electron-precise molecules would not be expected to act as electron donors or electron acceptors. Carbon cannot achieve an expanded octet. However, the other members of group 14 can form species with expanded octets due to the presence of unoccupied d orbitals. For example, silicon, germanium, and tin all form complex ions with sp3d2 hybridization around the central atom as shown here. All the group 14 elements form oxides when heated in oxygen. For example, if wood charcoal is strongly heated and placed in a glass jar containing oxygen, carbon dioxide will form. There are two main types of oxides: monoxides and dioxides. It should be noted that silicon monoxide is found only at high temperatures. In general, the higher the oxidation number of a group 14 element, the more acidic the resulting oxide will be. Thus, we observe that carbon dioxide, silicon dioxide, and germanium dioxide are all acidic oxides. The dioxides of tin and lead are amphoteric. For the monoxides, carbon monoxide is neutral, while germanium monoxide is acidic. Like the dioxides, the monoxides of tin and lead are amphoteric in nature. Try to answer this question on your own before checking the answer. Which group 14 element forms the most acidic dioxide? Answer: carbon dioxide is the most acidic dioxide in group 14. In water, carbon dioxide reacts to form carbonic acid, H2CO3, a weak acid. Carbon, silicon, and germanium do not react with water. Tin will react with steam in a single replacement reaction, as given here. Lead does not react with water, most likely due to the protective oxide film that forms on the surface of the metal. The group 14 elements react with halogens of group 17 to form halides. With the exception of carbon, they can react directly. For example, the reaction of silicon with chlorine produces silicon tetrachloride. Germanium, tin, and lead are able to form halides with the general formula MX2. The stability of these halides increases down the column. Most of the halides with the general formula MX4 are essentially covalent in character. The exceptions are the tetrafluorides of tin and lead, which are ionic. In the MX4 halides, the central atom exhibits sp3 hybridization with a tetrahedral geometry. The tetrachlorides of the group 14 elements, with the exception of carbon tetrachloride, are easily hydrolyzed by water by involving unoccupied d orbitals. For example, consider the hydrolysis of silicon tetrachloride. The silicon atom in SiCl4 accepts a lone pair of electrons from a water molecule, forming SiCl3OH and HCl. This process then continues 3 more times, eventually forming SiOH4. As the smallest member of the group, carbon exhibits some anomalous behavior as compared to the rest of the family. This is due to its higher electronegativity and ionization energy. as well as the lack of vacant d orbitals. Carbon has only s and p orbitals available for bonding, and therefore can only accommodate 4 pairs of electrons. Unlike the other group 14 elements, carbon cannot achieve an expanded octet. One unique property of carbon is its ability to form multiple bonds. Carbon can form double and triple bonds with itself and with other small atoms such as oxygen, sulfur, and nitrogen. These multiple bonds are pi bonds caused by the sideways overlapping of the p orbitals. Because of their larger orbitals, the heavier atoms in group 14 do not overlap effectively, and so do not exhibit this type of pi bonding. Another notable property of carbon is its tendency to covalently link with other carbon atoms to form chains and rings. This is called catenation. The carbon-carbon bonds are very strong. As a result, elemental carbon exists in several allotropes, and organic compounds have a wide variety of possible structures. The tendency to show catenation decreases down the group. Silicon shows a less ability for catenation than carbon, followed by germanium and tin. Lead does not exhibit any catenation. What do we mean by the term allotrope? Allotropes are different forms of an element which have different physical properties but identical chemical properties. Different allotropes of the same elements have different arrangement of the atoms. Carbon exists in both crystalline as well as the amorphous forms. There are 3 important crystalline allotropic forms of carbon: diamond, graphite, and fullerenes. Diamond, the first allotrope of carbon, is the hardest substance on Earth. Diamond has a crystalline lattice in which the carbon atoms are arranged in a rigid 3-dimensional network. In diamond, all carbon atoms exhibit sp3 hybridization. Each carbon is bonded to 4 other carbon atoms situated tetrahedrally around it. The CC bond length is 154 picometers. This directional network extends in space and produces a 3-dimensional network of carbon atoms as shown in the illustration. Try to answer this question yourself before proceeding. The carbon atoms in diamond are covalently bonded. Why is the melting point of diamond very high? Recall that each carbon in diamond is attached to 4 other carbon atoms surrounding it. It is very difficult to break up this covalent network as it is very rigid, and hence diamond melts at an extremely high temperature. Since there are no free electrons in a diamond crystal, it is a bad conductor of electricity. Another important allotrope of carbon is graphite. You are probably the most familiar with this form of carbon for its use in pencils. Despite the name, pencil leads are actually made of graphite. Graphite has a layered structure. These layers are held together by the weak van der Waals forces of attraction. The distance between any 2 successive layers is 340 picometers. Each layer of graphite is made from planar, hexagonal rings of carbon atoms as shown in the diagram. All the carbon-carbon bonds are 141.5 picometers in length. Each carbon in graphite is sp2 hybridized. Each atom forms 3 sigma bonds with its 3 neighboring carbon atoms. The 4th electron of each carbon is involved in pi bonding, using the unhybridized p orbital on each carbon atom as shown in the illustration. The electrons involved in the pi bonding are delocalized. This means that they are free to move, and thus graphite is a good conductor of electricity. Try to answer this question on your own before proceeding. Why is graphite soft and slippery? The layers in graphite are held together by the weak van der Waals forces of attraction. Thus, the layers slide past over each other and break off easily. When you take notes with your pencil, you leave layers of graphite behind on the paper. The third important allotrope of carbon, the fullerenes, are the most recently discovered. They were identified by Robert Kerr, Harold Kroto, and Richard Smalley in 1985, for which they were awarded the 1996 Nobel Prize in Chemistry. Fullerenes can be prepared by heating graphite in an electric arc in the presence of inert gases. This work led to the discovery of the 2 most important fullerenes: molecules containing 60 and 70 carbon atoms, respectively, plus traces of other fullerenes. Fullerenes are cage-like molecules. C60, or Buckminster fullerene, named after the American architect famous for his geodesic dome structures, looks like a soccer ball. It is sometimes referred to as a buckyball. Buckminster fullerene contains 60 carbon atoms arranged as a hollow sphere. This ball-shaped molecule has 60 vertices, each occupied by a carbon. It contains 20 6-membered rings and 12 5-membered rings. A 5-membered ring is fused with only 6-membered rings, while a 6-membered ring is fused with 6 or 5-membered rings. All the carbons in the Buckminster fullerene molecule are sp2 hybridized. Each carbon atom forms 3 sigma bonds with its 3 neighboring atoms. The remaining electron in each unhybridized p orbital of carbon is delocalized in molecular orbitals, giving the aromatic character to the molecule. 2 different bond lengths are observed in Buckminster fullerene. The carbon-carbon single and double bond lengths, as observed in C60, are 145.3 and 138.3 picometers, respectively. Each carbon atom forms formally 2 carbon-carbon single bonds and 1 carbon-carbon double bond. Under standard conditions, graphite is the thermodynamically most stable allotrope of carbon. Since it is considered as the standard state of carbon, its heat of formation is set at 0. Both diamond and fullerenes have higher heats of formation, reflecting their lower stability. The heat of formation of diamond is 1.90 kJ per mole, and the heat of formation for fullerene is 38.1 kJ per mole. The amorphous forms of carbon include carbon black, coke, and charcoal. Carbon black is formed by burning hydrocarbons in a limited supply of air, or by incomplete combustion. It is an almost pure form of amorphous carbon containing 98 to 99% carbon. Coke is formed when wood is heated at high temperatures in the absence of air, which is called the destructive distillation of wood. To form charcoal, coal is heated at high temperatures in the absence of air. Carbon has a wide variety of uses in its elemental forms. Diamond is widely valued in jewelry. They are measured in carats. 1 carat is equal to 200 milligrams. Diamond, both natural and synthetic, is used as an abrasive in sharpening tools, die making, and in the manufacture of tungsten filaments for light bulbs. Graphite is used as a dry lubricant in machines running at high temperature where oil cannot be used. Graphite is also used to make strong and lightweight composite material for tennis rackets, fishing rods, aircraft, and canoes. Being a good conductor, graphite is used to construct electrodes for use in batteries and in industrial electrolysis. Crucibles made of graphite are inert to dilute acids and alkalis. Activated charcoal is very porous and can absorb many times of its own volume of gases. It is used for adsorption of poisonous gases, removal of organic contaminants from water, and for odor control in air conditioners. Carbon black is used as a black pigment in black ink and as a filler in automobile tires. Coke is used as a fuel and as a reducing agent in metallurgy. We'll start with the oxides of carbon. Carbon monoxide with the chemical formula CO, and carbon dioxide Carbon monoxide is a colorless, odorless gas that is nearly insoluble in water. The carbon monoxide molecule contains 1 sigma bond and 2 pi bonds, as shown in the illustration. There are several ways to prepare carbon monoxide. The first way is the direct oxidation of carbon in a limited supply of oxygen or air. The reaction shown here is an example of incomplete combustion. Another way to prepare carbon monoxide is the dehydration of formic acid, also known as methanoic acid, with concentrated sulfuric acid at 373 Kelvin. On a commercial scale, carbon monoxide is prepared by passing steam This reaction produces carbon monoxide and hydrogen. This mixture of carbon monoxide and hydrogen is called water gas or synthesis gas. If air is passed over hot coke, nitrogen is produced along with carbon monoxide. The resulting mixture of carbon monoxide and nitrogen is called producer gas. Water gas and producer gas are important industrial fuels. The carbon monoxide in these mixtures can undergo further combustion. This produces carbon dioxide and liberates a great amount of heat. Carbon monoxide is a powerful reducing agent. When exposed to metal ores, it reduces most of them to the elemental form of the metal. Note that carbon monoxide cannot reduce the alkali and alkaline earth metal oxides, aluminium oxides, and the oxides of certain transition metals. Reactions with carbon monoxide are used to extract many metals from their ores. The reactions here show iron 3 oxide and zinc oxide producing iron and zinc. In the process, carbon monoxide is oxidized to form carbon dioxide. Since the carbon in CO has a lone pair, it can act as an electron pair donor. Therefore, carbon monoxide can react with certain metals when heated to form metal carbonyls. Several types of metal carbonyls are illustrated here. It binds to the Hem group of hemoglobin 300 times more strongly than oxygen. The hemoglobin molecule is, thus, prevented from transporting oxygen. This can ultimately lead to death if not treated promptly. Home carbon monoxide detectors are available and can be life-saving. Now let's turn our attention to carbon dioxide. Carbon dioxide is also a colorless, odorless gas, but it is non-poisonous. It has very low solubility in water. By volume, 0.03% of the Earth's atmosphere is carbon dioxide. Try to answer this problem on your own before proceeding. Consider the carbon dioxide molecule. What is the hybridization of the carbon? How many sigma and pi bonds are present in the molecule? The carbon in CO2 is sp hybridized. The molecule has a linear geometry. As shown in the illustration, the sp hybrid orbitals overlap to form a sigma bond with each oxygen atom. Each unhybridized p orbital on the carbon overlaps with an orbital on each oxygen to form a pi bond to each oxygen. Notice that the pi bonds are at an angle of 90 degrees to each other. The most important Lewis structure for carbon dioxide has both the oxygen atoms double bonded to the central carbon atom. The carbon-oxygen bonds are 115 picometers in length. The carbon dioxide molecule is non-polar. Although the carbon-oxygen bonds are polar, the bond dipoles cancel. Two other resonance structures shown here can also be drawn for carbon dioxide. There are several ways to prepare carbon dioxide. One way is by the combustion of either carbon or carbon-containing fuels such as methane in excess air. In the laboratory, carbon dioxide can be prepared by reacting dilute hydrochloric acid with solid calcium carbonate. On a commercial scale, carbon dioxide can be prepared by heating limestone, CaCO3, until it decomposes. In water, carbon dioxide reacts to form carbonic acid, H2CO3. Carbonic acid is a weak diprotic acid. It dissociates in two steps. First, carbonic acid loses one hydrogen ion to form a hydrogen carbonate ion. Then, the hydrogen carbonate ion loses its hydrogen ion, resulting in a carbonate ion. Both carbonic acid, a weak acid, and hydrogen carbonate, a weak base, are present in blood. Having a weak acid with its conjugate base forms a buffer system that maintains blood pH between 7.26 and 7.42. It is very dangerous for the blood pH to fall below the normal range. By using chlorophyll, plants make their own food through photosynthesis. This process removes carbon dioxide from the atmosphere. The ultimate product of photosynthesis is the glucose molecule C6H12O6. Heat from the sun warms the earth. Radiation is re-emitted and then reflected by the Earth's atmosphere. This is called the greenhouse effect. There are increased concerns that rising CO2 levels in the atmosphere may be contributing to global warming. Dry ice is the common term for solid carbon dioxide, which can be formed by allowing liquefied carbon dioxide to expand rapidly. It is used as a refrigerant for ice cream and frozen foods. Carbon dioxide has many uses. It is used to prepare carbonated beverages. Because it is heavy and does not support combustion, it is used in fire extinguishers. It is also used in the manufacture of urea, CN2H4O. Quartz has piezoelectric properties. This means that quartz can generate an electric field when mechanically stressed. This property of quartz is used to manufacture extremely accurate clocks. Quartz is used in modern radio and TV broadcasting as well as in mobile radio communication. Silica gel is used as a drying agent and as a support for catalysts and chromatography columns. Kieselguhr, a form of amorphous silicon, is used in filtration plants. Silicones are another important class of silicon compounds. These organosilicon polymers have a monomeric unit of R2SiO, where R is an alkyl group that repeats many times. Let's see how silicones are manufactured. First, methyl chloride, CH3Cl, is reacted with silicon in the presence of a copper catalyst to form methylated silicones. In addition to the dimethyl dichlorosilane shown here, trimethylchlorosilane and tetramethylsilanes may also be produced in small amounts. Next, the dimethyl dichlorosilane is hydrolyzed, as shown in the reaction. Finally, the straight-chain polymer is formed by condensation reactions. To control the length of the polymer, adding trimethyl chlorosilane blocks ends the chains. Silicones are water-repelling in nature. Due to the repetition of non-polar alkyl groups along the chain. This makes them useful for waterproofing fabrics. Silicones generally have high thermal stabilities, meaning that they are stable in high temperatures. They have high dielectric strength, which means that they can withstand high electric fields without breaking down. They are essentially inert chemically. They are resistant to oxidation and to most chemicals. These properties of silicones make them very useful. Silicones are used as sealants, greases, and electrical insulators, as well as for waterproofing fabrics. They are also used for surgical and cosmetic implants, as they are biocompatible. Silicates are another important class of silicon compounds. Many silicates are found in nature, including feldspar, zeolites, mica, and asbestos. The main structural unit of silicates is the ion, SiO4-4. This polyatomic ion has a tetrahedral geometry around the central silicon atom. The tetrahedral units of silicates may be joined together at the corners by sharing oxygen atoms. Silicates are thus able to form chains, rings, sheets, or three-dimensional networks, as illustrated here. Two important silicates are glass and cement. Aluminosilicates form when aluminium atoms replace a few silicon atoms in silicon dioxide. Since an Si atom with a +4 oxidation state is replaced with a +3 aluminium ion, cations such as sodium ion, potassium ion, or calcium ion are needed to balance the charge. Zeolites are hydrated aluminosilicates. They are microporous, with tiny cavities in their structures, as shown in the illustration. Zeolites have a variety of uses. They are used as catalysts in the petrochemical industry. For example, in the cracking of hydrocarbons. They are also used in isomerization reactions. For example, ZSM5, shown here, is used to convert alcohols directly into gasoline. Zeolites are also used as ion exchangers to soften hard water, that is, water with a high mineral content, especially calcium and magnesium ions.